All right, chapter 1, we're going to be beginning with section 2, and this is going to be broken up into 2 days just because there's a lot of information that needs to be reviewed and covered. Some of this may be review, some of it might be brand new stuff. Today's mostly should be review, talking about what functions are, talking about function notation, and then reviewing what domain and range are. And then tomorrow we will focus in on a few other key components of looking at functions. So first of all, what is a function? It is it's a relation of numbers. And a relation is a function if and only if for every independent variable, which we're talking about the inputs there, there's exactly one dependent variable, which are the outputs. Inputs and relation that we're talking about here is we're talking about a set of ordered pairs. We're talking about a graph. Here I have examples of some mappings. And a relation is just taking two numbers and pairing them up with one another. So in the mapping to the left here, hopefully you can see that each input is matched up with exactly one output. So 4 is matched up with 1. So 4 is an input, 1 is an output with the way that the arrows are pointing here. 5 is matched up with -3, 6 goes with 5, 3 goes with -2, 9 goes with 7. Every input has exactly one output. Now, if you look over on the mapping to the right, 9 goes with 7, 3 goes with -3, 6 goes with -2, 5 goes with 5, and where our problem exists is when we look at 4 and the fact that 4 is going to both 1 and it's going to +3 there, or sorry, -3. And so because our input here of 4 has two outputs, -3 and 1, this is not going to be a function. If we take a look at a function as a graph, here you're again looking for each input has exactly one output. And you'll remember that what we may have used, or what you probably used in Algebra 1 and 2, is something called the vertical line test. And the vertical line test can be used to figure out if you have a graph that is a function or not. And all it takes is just drawing out a vertical line and then taking that vertical line and moving it throughout the graph. As long as that vertical line only touches your graph at one point, that means that your graph is a function, because for each x value you have exactly one y value. Now if I go over to the second graph here, right now it's crossing at one point, but then all of a sudden I get to a problem here where now it's crossing at 3 points. So if I were to say here, okay, let's say x is at -1, well at -1 it has 3 different y values that are in existence here, so therefore this is not going to be a function. Another way that you can determine a function is just by looking at some ordered pairs. And you're going to be looking at essentially your x values and checking to see that none of them are repeated. So here I've got 5, 7, -4, 3, 9, -1, 0, 6. Every x value has one y value to it. Now where I get a problem on the next one here is I've got 7, -2, 5, 0, -4, 8, and 5, -3. Well, hopefully you can see our problem is going to be right here at 5. If I was to graph these out, I would have a point at 5, 0, and then I would have a point almost directly below it at 5, -3. With those 2 points right there, they would not cross the vertical line test. And this here is saying that if I put in 5, I have 2 possible outcomes, which makes this not a function. And I just need to add something to this slide real quick, so I'm going to pause. All right, so now as we start looking at functions, really this entire semester we're going to be looking at a lot of different functions, and these are just 6 of the few that we'll be looking at. We've spent a lot of time in years past working with linear functions, which are straight lines. Notice it passes the vertical line test. We've spent a lot of time with quadratic functions. Again, passes the vertical line test. You've worked a little bit with exponential functions. We'll spend a lot of time with those this year, and then logarithmic functions as well. There's also the cubing functions, and what will be new to you is the trigonometric functions that we'll be using. So all of these 6 here, and there are more than this, all follow the vertical line test, so therefore we do call them all functions. So where do we go with functions? We are going to now talk about using function notation. And function notation is just a fancy way of writing out a problem instead of using the y equals. It also allows us to give a name to the function, kind of like a nickname, so that we can address it by a letter of the alphabet rather than reading out the entire equation itself. So here I have y equals 2x plus 1, and I can name that function by using this notation here, which is not f times x. It's saying f of x equals 2x plus 1. So this is just reading f of x equals 2x plus 1. It's just giving it a name so that later on we can talk about more than one function. How we use function notation: if I wanted to evaluate f of 5, I would take this 5 and I would replace the value of x for it. So I would take 2 times 5 plus 1, so give me 10 plus 1, and I would end up with 11. So that's evaluating the function. If I want to evaluate f of negative 6, I would do the same thing. This time plug negative 6 in for x. So I would get negative 12 plus 1. So I would end up here with negative 11. And there's my two answers that I'm looking for. Now the reason that we use the functions here is so that, or we give them names, is so that you can address more than one. So here I have three functions that we're looking at, and I have function f, function g, and function h. This way I can use the names of the functions rather than saying, okay, function 4x squared plus 2x. I can just say function g instead. And then we can also do some different evaluating. So if I wanted to go ahead and evaluate what f of negative 2 is, I could go to function f here, and which is 3x, so take 3 times negative 2, and we would end up with negative 6. If I wanted to take a function here, and we're going to take function h, and this time I'm going to take function h, and I'm going to take h of p. Now what this is doing here is it's putting a new variable into your function. So I'm going to take function h here, and where I see my value of x, I'm going to replace it with a p. So now I have 3 times 5 to the power of p. Problems that you want to be real careful about is I'm going to go ahead and take g of x plus 1. And what I'm doing here is I'm going to use function g, and I'm going to take that x plus 1 and put it in for both x values. So I'm taking 4 times the quantity of x plus 1 squared plus 2 times x plus 1. And from here, everyone usually starts out really strong with a problem like this, but then we just have to be really careful as we evaluate, because remember that when you take a value and you square it, a sum or difference, most importantly, you have to expand and use FOIL for this problem. So here I'm going to get 4 times the quantity of x squared plus 2x plus 1, and then I've got plus 2 times the quantity of x plus 1. So how I got x squared plus 2x plus 1 is by FOILing that out and simplifying. Now I can use my distributive property, 4x squared plus 8x plus 4, and distribute over here 2x plus 2, and now we can combine like terms, and I get 4x squared plus 10x plus 6, and that is what g of x plus 1 is. So that's evaluating functions. So now moving forward after functions, we want to be able to review what domain and range are. And domain and range is a really, really, really important thing to understand and to be working with, because it's going to come up a lot down the road here, and we really want to get a good understanding of what domain and range is asking us to find. So the way that I thought I'd remind you about this is kind of think about something going up in the air and coming back down. When you're talking about the domain, if I have a rocket that's going up in the air and then coming back down, the domain is telling you how long the rocket is in the air for. And so what I would want to look at here is what's along my x-axis. And so because I can't have negative time for a rocket being in the air, I can say here that my rocket is starting at 0 seconds. And then it went up in the air and it came back down, and it took 10 seconds for it to get down to the ground. So usually people are going to say, okay, it took 0 to 10 seconds, so that's the domain. What we just want to do here is put it as an inequality instead. So time, usually represented by t, is greater than or equal to 0, less than or equal to 10, and there's our domain. It's the values of the x. Then comes our range, which is telling you what heights does the rocket reach. And so it started at 75 feet, went up to 100 feet, and then came back down. So when we're talking about the range here, we're talking about the y values. And so again, what a lot of people are going to say here is they're going to say, okay, the rocket went anywhere from 0 to 100 feet. Well, we're going to write this out as an inequality instead. So the height, which is less than or equal to 100 feet, was greater than or equal to 0, since it can't be at a negative feet because it's going to hit the ground. So domain is along the x-axis, range is typically along your y-axis. And now we're going to look at just the definitions here that I have, and then we'll also look at some more graphing examples. So domain is the set of all input values for a function. So we're talking about the independent variable. So that's all of your x values on your ordered pairs. And your range is going to be the set of all the outputs, which is the dependent variables of your function. So that's going to be all the y values. So you'll notice that I have those highlighted in red for your domain and for your range. Now we're going to be looking a lot at graphs and trying to determine what the domain and range are of these. And one thing that I like to have people consider is just thinking of maximums and minimums, because I think that's a way to look at domain and range and have it kind of make some sense. So if I look at the first graph here, the fact that I do not have arrows on our graphs means that we have endpoints, so they do not go on forever and ever and ever. Well, so now when I'm looking at the domain, I need to look at what is the largest x value that's possible and what's the smallest. Well, as far as the smallest value goes, the furthest to the left that my graph goes here is at 1, 2, 3, 4, is at -4. So it does not go any further than that. And the largest value that x goes to is +2. So when I'm thinking about what my domain is, I want to consider the fact that my smallest x value is -4 and my largest x value is +2. And my domain is everything that's in between there. So my x values here are less than or equal to +2, greater than or equal to -4. And there's my interval. As far as the y values go, or for your range, we're talking about the y's. So we want to find the smallest y value that's possible, which is our minimum, and that's at -1, -2, 3, 4, 5, 6. At -6 is going to be our smallest. And then if I look at what my maximum is going to be at here, and I count that up, I'm going to end up with 7. So going from -6 to 7, that's my range. And you'll notice that it fits in a nice little box here. So our y values for our range is going to be anything that's less than or equal to 7, but it has to be greater than or equal to -6. And there's our domain and range. Looking at the next one here, we want to find our minimum for your x values, and you want to find the maximum for those. So our minimum here would be at -6, and the maximum would be at +7. This is saying that my domain has to be greater than or equal to -6, but less than or equal to +7. If I look at my range, take the smallest y value, and take the largest y value, which is going to give me -8 and +9. So our y values are anywhere between 9 and -8. With the last one that I have here, again, the domain is just based off of your x values. So the smallest x value I have is -1, and the largest x value that we have here is 5. So our domain is going to be less than or equal to 5, greater than or equal to -1. And then we're going to look at our y values. our smallest possible value and our largest possible value, which smallest is -7 and the largest is 4. So y is less than or equal to 4, greater than or equal to -7. So we want to be able to write this out in the inequality notation and just be looking for what are your minimums and your maximums. Now, not many graphs look like this and have two endpoints. More so, the graphs you're going to be looking at are going to be going on forever and ever and ever. They're going to be some sort of line that goes in sort of one direction and is continuous. So we have to be real careful about problems like this, because these lines that I have drawn here, now they look like they end, but really because it's got that arrow to it, this line here is actually going to keep going forever and ever and ever and ever. So I don't have an endpoint in sight for your x maximum. Now I do have an x minimum, which is going to be right here at -4. But the fact that I don't have an x maximum, I'm going to put it, it's going to go to positive infinity, because that's what it's going to do. This line right here is going to keep going forever and ever and ever in the positive direction. As far as its y value goes, I do have a y minimum, and that's at -6. And then as far as our y maximum, you have to be careful, because the y maximum is not going to be at, let's see, 1, 2, 3, 4, 5, 6, 7. Okay, this right here, that's not your maximum, because it's going to go past that. And because it's going to go past that non-forever, our y maximum is really going to go towards positive infinity. So when we talk about our domain and range, we're not going to use this infinity symbol, because that's just saying it's going on forever. We're going to say here, since -4 is your minimum, that your values of x here have to be greater than or equal to -4. With your y values here, since y is your minimum once again, going towards infinity, we're going to say that y is greater than or equal to -6. So it's going to be greater than or equal to these two values and go on towards positive infinity. If I look at the next one here, because I have an arrow going in both directions, to the left of this graph and to the right, our x minimum is -infinity. It's going to keep going. There is no minimum x value. With the maximum x value, there is no maximum there either. It's going to go on forever. And so what this is doing here is it's saying that every single number is possible, which is all real numbers. Any number here is going to work for your domain, and how we can write that out too is a little funky little r, which is saying that all real numbers work for this function, for your domain. Now for your y values, you might think, oh, every number works. Well, we have to be careful, because for this graph here, we do have a minimum. Now as far as the y maximum goes, that's positive infinity, but we do have a y minimum of -8. And since we're going towards positive infinity, y is going to be greater than or equal to -8 in this problem. In the last problem, I have a straight line that is going on forever and ever in both directions. And because of that, that's going to give us a x minimum value of -infinity and an x maximum value of positive infinity, because they're going to go on forever. Your y's are going to be the exact same, because there is no minimum and there is no maximum. They're going to go on forever. So what this is telling us here, that your domain is made up of all real numbers, any number that's on the x-axis, whereas your range is also going to be real numbers, which is any number that's along your y-axis. So we've gone over domain and range. We've talked about functions, and that's where we're going to leave it for the first part of section 1-2. If there's anything that you have questions on, make sure that you write those down, and we'll take care of those questions in class tomorrow.